Oh, yeah. Hold on. I'm using the wrong hand. Get out of Emacs just by pushing all of the keys at once, I think, right? Is that? Oh no, what did I do? All right, well, okay. Anyway, I can only do this one-handed, so. Okay. Good morning. This is the IEPG at IETF 106 in Singapore. If you're not supposed to be in Singapore, I'm sorry you took the long flight. If you're not supposed to be in the IEPG and you're supposed to be at some other meeting, then you're in the wrong room. You should consider moving, or you could stay because it will probably be fun. For those people that are presenting, there's a microphone. Please don't do this. Please speak into the microphone. There's a nice thing. We'll show you the pictures that are up there so you don't have to do this. Okay. There's also a pointer. Whee! The clicky thing doesn't work. My laptop is misbehaving or something. So you can at least point. We have 5 presenters, 5 presentations. First up, Carlos. Oh, by the way, my name's Chris. And Warren's not here. He's busy with something else. Hello, everybody. You just say click.
Oh, next.
You say click.
I say click? Okay. Man, you're tall.
You can readjust that.
Okay. Okay. Well, good morning, everybody. Actually, thanks, Chris, for the time. This is just a short introduction, a short, I would say, marketing presentation. I want to introduce you a new RPKI validator. We call it FORT because it made sense at the time and it said something about the stronger internet or something, but we just call it FORT and we try to not think very much about what it means. So there's a background to this. There's the FORT project and the FORT validator. The FORT project started as an initiative to promote routing security in the region. There was a call from the Open Technology Fund, which is a fund that finances technology projects having to do with freedom on the internet, which I think is something we all sympathize with. And back at the time, we were toying with the idea of developing a new RPKI validator, and we were in discussions with the great guys from NIC Mexico about developing something. And at some point, everything came together, and we decided to move forward with this project, which has 2 components. It has a validator, and it has something we call the tracking tool, which is hopes to be, when it's ready, a system or mechanism to keep track of routing incidents in the region. And that is, I mean, I would say, social part of the Open Technology Fund project, which is that is the part that interests them the most. The idea is the tracking tool will provide information about routing incidents for non-technical people, under the hope that it will help people realize whether their country, government, ISP, whatever, is actually, playing tricks on them. Next, please. So what I'm going to talk about today is the RPKI validator, which I said is one of the 2 parts of the project. Next, please. Why another RPKI validator? Lately, it seems to be that everybody is developing a new RPKI validator. There is at least 4 projects that I can remember about. And I think it's good. Having diversity is good. Having programming languages diversity is good. And it's also worth mentioning that back at the time when we decided to move forward with this project, well, the options about RPKI validators were rather limited. So it made a lot of sense at the time to create a new one. Next, please. So, short description about Fort. What it's implementing right now is repository validation and the RTR server. There's no GUI, there's no web, there's no nothing. So it's basically something you run and hopefully you don't get anything on the console, right? So it's rather unexciting in that sense. It's written in C, which I think it's great. I mean, I didn't know people still did strong programming in C. I mean, people, I thought everybody had moved to Go and Rust and Python and things like that. It compiles cleanly and runs on several Linuxes and BSD platforms. The license is MIT, so basically it's almost, you can do whatever you want with it. And the roadmap as it stands is we are now at version 1.1, and the guys from Link Mexico are planning a version 1.2 for the first quarter of 2020. The code is in GitHub, that we have the URL. Next, please. What does it support right now? You can check the details on that URL. There's a very nice table with all the RFCs and the percentage of implementation, but basically some of the things that I consider interesting in this validator is that supports Slurm, it supports the JSON files from the RFC, it supports validation reconsider, validates Ghostbusters, it supports policy qualifiers, and has some support for BGPsec objects. What is missing notably is our RDP support and the HTTPS styles. Hopefully coming in version 1.2 in a few months. Next, please. It has reasonable high test coverage. This is some of the platforms where the tests have been run. I haven't tried compiling it on BSD, but I guess it's the same thing as always. It's very easy to install it on Debian on Ubuntu. Next one, please. The usual routine, right? You install some dependencies, you unpack the code, configure, make, install, and you're running. I created a couple of Docker images you can try if you want. Next, please. There are two ways of running it. One is what in the documentation is called a standalone, which is basically it will run, validate a repository or a set of repositories, produce some CSV output, and exit. No fancy web, no graphics, nor anything. And the other way of running it is with the server, with the RTR server enabled, and it will just stay there. And the only thing you'll hear from it is whether it finds errors and or some inconsistency in the repositories. These are the basic options. It has tons of options. Some of them are quite interesting. For example, you can tune a little bit how strict the validation it performs, which I think is kind of nice because there are still some, I would say, divergences in the implementations of the repositories. Next, please. A few tests that I run. This is memory consumption running on a standalone mode. These are the dark blue is APNix repository, light blue is LACNIC, and the sort of yellowish, greenish something color there is Afrinix, the repository. It's quite low. It's quite efficient in its memory usage, which is kind of nice, and it's, I would say, a natural byproduct of it being written in plain C. Next. Well, thank you. If you like the idea of having a new tool in your tool chest, please send us your bugs. I'm not promising this is the greatest thing since sliced bread, nor that it's bug-free. It's probably full of bugs. That is what we are mostly interested in hearing from you. Send us your bug reports, and if you like it, please let us know. Thank you.
Questions to the mic, please.
Randy Bush, Arcus and IETF. Randy Bush, Arcus and IETF. How do I deal with inter-instance Slurm? In other words, I have a Slurm file in my POP in San Diego, and I want you to run it in your POP in San Francisco. What's the trust model?
That's a completely different discussion. I kind of agree with you, but I don't know. You have something red in your hair? Or is it the light? No, seriously. Okay. Okay. Thank you.
All right, next up, Yoshiro. I don't know why your first slide doesn't show up.
Yep.
But just say click. You could point with that. That doesn't work. You have to say click.
Just click.
Yeah.
So I want to get back to the first.
Yeah, I don't know this. That's weird. So that it shows. Oh, there we go. Now it's showing. Wait, no. Oh, okay. How about that? And it won't work. It's just here.
Oh.
Yeah. So just tell
So,
me.
Can you back to the title slide? No, one more.
Okay, good.
Hi, good morning. Okay. My name is Yoshiro Yone from JPRS. Today, I'd like to introduce our research work to detect the DNSSEC validation failure at the TLD server monitoring. Next, please. So, as you know, DNSSEC validation failure happens frequently, but the reliability of DNSSEC operation is a key of DNSSEC deployment. So that, next, please. Yeah, we made a research question. How can we detect validation failure rapidly and efficiently? Of course, active measurement is an easy way to detect DNSSEC validation failure, but it causes higher loader for more DNSSEC available domains. So that we thought about how can we detect DNSSEC validation failure by the passive measurement. So we focused on to see the change of query patterns could be a good indicator at the monitoring of authoritative name servers label. Next, please. So towards detecting validation failures with passive measurements, the goal of our research is detecting change of query patterns at CCTLD servers. At this moment, we are the JP operators, so we are seeing JP-DNS servers before and after failure. And current our work is using both active measurement and passive measurement. For the active measurement, we are using LIPE Atlas for the DNS client. And DNS validators are neighbor to the LIPE Atlas, approximately 500 at ISPs on edges. And also we are prepared local authoritative DNS servers which provide both successful DNSSEC validation and failed DNSSEC validations with different TTL settings. And passive measurement vantage point is JP-DNS servers. Next, please. This figure shows the measurement overview. The measurement period for this research is April 2018. This is also conjunction with DITL happened on April 2018. And passive measurement vantage point is JP-DNS servers. And active measurements at the local authoritative servers at the right bottom right circle is a local authoritative server provided third level of JP domain name. And the targeted queries from LIPE Atlas probe are NS, DNS key, and the DS records. And we use around 1,000 live address probe and 600 of DNSSEC validators at home. Next, please. So before we perform our measurement, we search for the public DNS because we do not know the concrete behavior of public DNS, and we are targeting the validators at ISPs and homes, so that we send live probe address unique queries to our authoritative servers and check the source address of the queries, which validators or resolvers sent to a query to our local servers, and check if it is in the public DNS server's IP address or not, so that we find which live address node uses the public DNS, and we excluded those live address probes from our measurement. Next, please. And we also measure the TTL distribution in signed.jp DNS .jp zones prior to our measurement. So we can find 4 categories of the TTL settings for NS and DNS keys. This quadrant shows the classification of the length of NS and DNS key TTLs. We don't know why this quadrant happens in Japan, but this is very typical to some industries. Next, please. So according to these TTL settings, we set up the 8 zones for this test. Next, please. Okay. So the 4 zones are successful validation, and 4 other 4s failure validation because of the inconsistency between DS and DNS key. And for this setting, we use the fixed TTL for DS and A records. Next, please. So this table shows the result of queries we observed at the local authoritative server, that is 3-level domain. And as you see, when DNSSEC validation failed, then overall queries increased in for DNSSEC related queries. So the left-hand side is a successful validators, successful domain names, and the right-hand side is a failed zones. So you can see several multiplies of each resource record queries. And so next, please. And this is the result of queries monitored at the JPDNS. As you see, when DNSSEC validation failure happens, DNSSEC related records queries are increased, but the attenuation is lower than the authoritative at the local servers. So next, please. But you can see DNS key is better indicators because especially for the longer TTL settings. For OK23 at the left-hand side and OK43 at the left-hand side is a longer TTL, and see the NG23 and NG43. It is also the shorter TTL. So the multiplies numbers is higher than the shorter TTL of DNS key. It's about 7 times higher than the successful ratio. So that we thought that the increasement of DNS key is could be an indicator. Next, please. So this table shows the comparison with local authoritative, that is third level authoritative, third level servers and .jp CCTLD servers. So you can see the huge attenuation of observable queries. So if we can see the local authoritative servers, we see much more queries, but we still see some increasement on the TLD servers. But it is sadly to say that the validation failure in minor domains are likely to difficult to detect. Next, please. So the conclusion of our research is we conducted DNS passive and active measurement to know query behaviors in DNSSEC failure. And DNS queries increased at DNSSEC validation failure. The attenuation of queries in DNS hierarchy is different as expected. But as you see, DNS key difference is still a good metric to detect validation failure. Next, please. So that we still continuing this work because we have still some unknown issues. So that was one of the issues, difference in public and other resolvers. Public DNS and other resolvers will have different behaviors because public DNS have very large and very good operation. And the quantify of CCTLD, that is top level or second level or third level attenuation. So because I am a TLD operator, so I am watching or monitoring the TLD servers mainly. And TTL effect in failure status. And we had to have some longitudinal analysis of a part of GPDNS server traces. And we want to have effective quasi real-time detection method at TLD server side because we are monitoring two out of 7 JPDNS servers almost real time, so that we can find we can use those 2 servers as an vantage point to detect of DNS failure. So I'm very welcome your any comments regarding to research work. Thank you.
Any questions? You're off the hook. Roy.
Hi, everyone. My name is Roy Arends. Before I start on this topic, a disclaimer. I work for ICANN, and all opinions expressed here are my own, not necessarily ICANN's. Just want to make that clear. I'm going to talk about private space names. A lot of you are thinking now, not again this private name stuff. We talked about internal, we talked about .alt. Can we just move on? Well, next slide.
No idea.
Yes. There you go. Thank you. Yeah. So if you look at the solution space currently, there are a lot of solutions out there. People suggest that you register your own name. Well, that's not really private. Before I go on, let me explain quickly what I mean with private use. It's a name that you can use on your own private network, be it a corporation, be it your home network, etc., etc. Another argument is don't do it. Well, I've often heard that, but that also really doesn't work. Use .internal or .local or .alt or .home, but I'm not really going to talk about .home, or home.arpa. And the problem is there is no defined way of doing this. Thank you. Can I have the next slide, please? And the result is something you see on the screen here. These are the results of these are the results of ITHI. ITHI is Identified Technology Health Indicators. In short, it's the stuff that we've observed at the LRoot or IMRS root server, the top 13 names that do not exist that's been queried for. And you can see it's all over the place. There's nothing wrong with these strings. I'm just saying that we observe that these things leak and they do not exist in the root zone. Next slide, please. So I'm going to talk about a proposed solution space constraints. So now that we understand the problem space, here are some constraints on the solution space. We need a simple and concise BCP. A BCP that basically says, if you want to do this, this is a way of doing it. We need to have a label in there that has no semantic meaning. What I mean with semantic meaning is like, it shouldn't have a literal meaning, like internal or private or alt or local or home or anything for that matter. Because the moment you choose private or internal, folks have an argument when they say, well, that doesn't really cover my home network or my private use network. And remember the XMIME headers that I talked about before, right? Or in language tags, you have X-dash. Those are not semantic headers. They have no literal meaning. So we need something that has no semantic meaning. And we also, another problem with these strings are they're too Anglophonic. They don't work in German or in Dutch. It's also smart to choose a label that will never be delegated. And we also need to choose a label, with label I mean a top-level domain label. Choose a label that may not require RC 6761. This is the exceptionally reserved list of top-level domains. So maybe we can just use a 2-character ASCII domain. Next slide, please. This is a potential political minefield, 2-letter ASCII domains. So you can kill me later in the mic line. RC 1591 talks about domain name system structure and delegation. There's this infamous section or famous section that talks about country codes. The IANA is not in the business of deciding what is and what is not a country. The next section talks about the ISO 3166 list. And keep in mind that the next section, and actually the entire document, does not talk about countries at all. It talks about country names. And it talks about entities, but not countries. So ISO 3166 list, those are basically the 2-character top-level domains. Sorry, the 2-character country codes. Can I have the next slide, please? This is them all. I can go through them right now. It's AA, AB, AC. Anyway, I've counted them one by one. There are 676. I'm sure there's some mathematical tricks that you can use in order to do this faster. But there are 676. Next slide, please. What the ISO 3166 folks have done is they've categorized them. All of these individual elements fall into a category. And I'm a little bit colorblind, so I hope I'm going to get this right. Can I have the next slide? Yeah. On the top left, you see a colored square that says AA. A colored square, it basically means it's user assigned. This is what I'm going to talk about in a minute, but I'm going to go quickly through the rest. You have the white background. Is it actually visible? I know I'm perfect, that's visible. So the white background, like AB, those haven't been assigned yet. They may be assigned in the future, but they haven't been assigned yet. So the category is unassigned. Then we have exceptionally reserved. like UK, that's yellow, and EU, that's yellow. Small sidestep here. I used to work for a company named Nominet. And I used to work there for 9 years. And I knew UK is not GB, but I never knew the following. And this is only what I discovered in the last couple of months. ISO 3166, as you know, has UK as exceptionally reserved. And in the context of ISO 3166, it means that UK is not a country. Not a country name is not assigned, because ISO 3166 is assigning official country names to a 2-letter code, right? This UK is not assigned to the United Kingdom. Why not? It's because the ISO 3166 decided long ago to avoid generic terms like United or Kingdom or Republic. If you're going to stick with all these generic names like United, Kingdom, and Republic, you're going to soon run out of use, case, and Rs to use in your 2-letter domain. So for the United Kingdom of Great Britain and Northern Ireland, the first distinguishing string is Great Britain, hence the official encoding for the country code, for the country name United Kingdom, Great Britain, Northern Ireland is GB and not UK. So why is this exceptionally reserved? Sorry? Yes, that's an exception. Yes. So if you look at where was I? Let's move on. The other codes is the green stuff that's officially assigned, and then you have some transitionally reserved and indeterminately reserved. I'm not going to go into that right now, but it's just for me it's an interesting thing. Next slide, please. So these are the codes that I want to talk about. The user assigned stuff: AA, QM to QZ, XA to XZ, and ZZ. Next slide. So what does the ISO standard say about these things? About the construction of the Alpha 2 code, the ISO 3166 standard uses a combinations in the range AB to QL, RA to WZ, and YA to ZY. So the ISO standard talks about that range of codes. What did they say about the other 42, these user-assigned elements? They are not used in the standard. They are not used. They will never be assigned. They will never be reserved. They are not used. And this is important in the context of what I want to talk about in a minute. So the standard goes on in 8.1 about special provisions. Users sometimes need to extend or to alter the use of country code elements for special purposes. And then in 8.1.2, it says, if users need code elements to present country names, not countries, country names not included in this part, these series of letters, AA, QM, QZ, etc., are available. This is guidance. It doesn't mean you can't use this for anything else. And I'm going to give you a few examples of how other standards are using these things. Next slide, please. So how are these things used elsewhere, these user-assigned codes? ISO 3901, International Standard Recording Code. And I'm not going to pretend I know anything about these things. I've just found them. So it reserves ZZ for direct registrants independent of any country. Now the next one is quite interesting. ISO 4216, codes for the representation of currencies. It reserves XA to XZ for transactions and precious metals, as they are country independent. I'm going to talk about this a little bit. US dollar. The official code for US dollar is USD. And the US in USD comes from the 3166 standard. GBP. Remember GB UK? You don't have UKP, you have GBP. The GB in GBP stems from the ISO 3166 standard. So what's all this XA stuff? In official standards, gold can be used, sorry, not in official standards. In general, gold can be used to pay for stuff, right? It's currency and transactions, etc., etc. There's an official code for that. It's XAU. Silver, XAG. Bitcoin, I'm not kidding, XBT. So these are used, these private space names, these user-assigned names are used in all kinds of standards. ISO 6166 talks about access for security clears to Euroclear, Clearstream, etc. Away from the ISO standards, next slide please, you have ICAO, International Civil Aviation Organization. It reserves ZZ for UN travel documents. WIPO, the World Intellectual Property Organization, uses a whole range of these private space things. And it uses not for countries, but basically for their own offices. So if you have a patent or an application from a certain country, you can use a country code. But if it goes to a certain patent office, you can actually use the code for that patent office. Closer to home, the CAP form, the Certificate Authority and Browser form, it reserves XX to signify location not covered by ISO 3166. And even closer to home, an RFC 5646, well known to many of you, a text for identifying languages. This is when you use X, these language tags in your browser, etc., etc. Next slide. This is the text lifted from that standard, from that BCP. It says, for example, the region subtext AA, ZZ, and those in ranges, etc., etc. You recognize these from before. They can be used to form a language tag. And here's an example on the screen. So next slide, please. So in conclusion, we now have, I, because I speak for myself, have shown you that Alpha 2 user-assigned codes, these 2-character codes, they are used as intended in various standards, and therefore these codes will never be ISO assigned or reserved. It says so in the standard. That implies, if I follow RC 1591, it implies that these codes will never be delegated. And since they never be delegated, we may not, and I say may, happy to do it if that's needed, we may not need these to go through RC 6761, where you reserve them, such as .onion, etc., etc. And the cool thing, just like these XMIME tags, right, using these 2-character codes have no semantic meaning, which is a good thing. Next slide. So I'm just going to use this as a suggestion. I don't want to paint the bike set too much, right? To use ZZ. I'm going to use ZZ as an example going forward. Luckily, I only have one slide left. But I'm not suggesting that we should use this now. I'm just suggesting that ZZ is available for this purpose. Next slide. So what about DNSSEC? Well, we all know that ZZ doesn't actually exist. And so a validator will validate that ZZ doesn't exist because it doesn't. Right? A validator can prove this. That's a good thing. I don't want to be lied to, right? At least not without approval. Now, some have suggested that ZZ or internal should be delegated in the root unsigned. Now, I disagree. If I, as a validator, want to be lied to, I want to make that explicit. I want to have to configure it that people can lie to me. So .internal, .alt, .onion, or whatnot, if I want to allow that in my validator space, then I want to make that explicit. I want to have a trust anchor for that, a negative trust anchor. Now, Stubby works with that, Bind works with that, it all works, basically. So, and even better, if I want to have a signed private space, I can now do that with a positive trust anchor as opposed to a negative trust anchor. Anyway, this is my my rant, my little talk about using private space names. I will take this to DNS Ops on Thursday, and I will bore you all once again with this stuff. If you have any questions, let me know. I'm available all day, all week for discussions on this.
Just a quick comment. Thank you for this, and I think it makes a lot of sense. I've been using .xy for a number of years. I didn't do the detailed research. I just read the Wikipedia article on ISO 3166. The other proposals, I mean, .internal is nice, but it's just too long. I mean, it feels really unnatural to ping your, TV. The ping TV.internal. It feels unnatural. People are not going to use that. So thank you very much, and
all right,
we'll work.
Perfect. Thank you.
Nobody else? All right. Thank you. Job Snijders. No clicker. You must ask. Scream out. Next.
Good morning, IEPG. My name is Job Snyders. I work for NTT, and we're having random slides. Next slide, please. I want to give a bit of a recap on recent RPKI deployments, highlight a regional Internet Registry policy update that is of interest to this group perhaps, share some updates on an open source project, and finally conclude with an update about the best operating system on the planet. Next slide, please. So I have a server somewhere, and with a bunch of people, we're using that server to map out RPKI deployments on the internet using a fairly simple method. We have two prefixes. One is an RPKI invalid prefix. The other is valid. And from those prefixes, we send ICMP messages to every IPv4 address on the internet, and we compare which of the source addresses gets replies. Now, in this image, you see blue is IPv4 addresses that responded to both the valid and invalid source address. This means they are not performing RPKI-based BGP origin validation. And yellow is only responding to the valid source address. So they are, in fact, doing origin validation, or a network between that server and that IP address is doing origin validation. So this is a snapshot from August. Next, please. A month later. Next, please. And what you can see here is that RPKI deployment is rapidly picking up. The largest networks on the planet are deploying it. The smallest networks on the planet are deploying it. Route server operators are doing it. So that's a very cool development. Next, please. Now, an update on RPKI in context of a RAR. In the RIPE community, roughly a year ago, the IRR database was split into two parts. One was called RIPE, and the other is called RIPE non-off. And the split occurred because the IRR objects in the RIPE source were authenticated against the wishes of the resource holder, but there also was a bunch of data in the RIPE IRR that was never, in fact, checked against the wishes of the resource holder. So we call this non-authoritative. And that non-authoritative data set cannot just be deleted, because we don't really know which parts of that data set are still useful, which parts serve a purpose, and which parts are detrimental to operations. So the thinking was, what if we use this origin validation procedure and apply it to IRR objects? In other words, if an IRR object is in conflict with published RPKI ROAs, we can conclude that the IRR object is describing a state that should be rejected, and therefore this IRR object can be deleted. Now, the community came to consensus on this. This policy was ratified last week. And out of the 65,000-ish objects in this data source, roughly 900 are in conflict with published ROAs. If you want to inspect this, you can download a small Python script I wrote, and that will show you the data. Next slide. This is one of such examples. Probably sometime long before I was even walking this planet, a company created route objects that describe a state that is in conflict with ROAs that NTT published. And NTT did not have any way to delete these IR objects in the right database until now, because now we can point at the RPKI ROAs, which signify that objects like these should not exist. Next, please. Related to the policy that will be implemented in the RIPE database, is a effort called IRRD. And IRRD is becoming smart middleware between your prefix filter generation client and the various data sources that exist out there in the wild. Next slide, please. The reason IRRD4 exists is that legacy IRRD was no longer extensible. There were some reliability issues with this daemon, which meant that we just had to restart it every week. But the code was complicated, which meant that we could not add new features, specifically new security features. And one of the cool things that is coming to IRRD is a mechanism similar to what is happening in the RIPE database. The IRRD4 daemon in its next release will have functionality to consume RPKI data to suppress or delete conflicting IR information. And this will happen on two levels, both in context of the IRRD daemon being a authoritative, well, quote-unquote authoritative database, and on the mirroring level, when this daemon consumes data from other databases over NRTM. In both paths into the cache of this daemon, origin validation will be applied, thereby significantly cleaning up the potential damage that the IR can bring. Next slide, please. The beauty of this mechanism is that it not only helps us clean up the past, route objects that have been created in the last 20 years, it provides us operators with an industry standard mechanism to get rid of old route objects, but it also helps protect us going forward. Because the moment you put in RPKI ROAS, these daemons will reject IR updates that are in conflict with the published ROAs. So publishing ROAs becomes more valuable, so to speak, because it helps you clean up things, but it also helps you protect going forward. The timeline for these things is roughly spring 2020. I expect the various involved parties will provide more updates as these timelines become more firm. But the good news in all of this is that it's not too far away. Next slide, please. Now, onwards to OpenBSD. OpenBSD is a research project where we experiment with things. And amongst those things is RPKI nowadays. You have to realize OpenBSD is not only very useful to create beautiful slides like I have done here, but it also is a functional network operating system, meaning that if you install this software out of the box, you have a BGP implementation, an OSPF implementation, a decent MPLS stack, including layer 3 VPNs and pseudo-wires and whatnot. And from that context, it is very interesting to experiment with the notion of creating a network operating system that out of the box can perform RPKI-based origin validation. So we set out to write a validator called RPKI client, but this was not a trivial effort. LibreSSL, the cryptographic core that is used in OpenBSD, which is a fork of OpenSSL, did not have capabilities to handle CMS. So that had to be added to LibreSSL, and the developers were giving me a lot of shit for it because it turns out CMS is not trivial to implement. Furthermore, we had to implement rsync. This project is called OpenRSync. And those three components have created a scenario in which we can have origin validation out of the box. Can you do the next slide? Here's a small screen capture. The BGP daemon is running. From cron, I am calling the RPKI client that outputs a list of the VRPs into a text file formatted suitable for OpenBGPD. And this allows the BGP daemon running on this box to do origin validation and show us valid or invalid states. Now, my hope is that by implementing RPKI at this level in a network operating system, we inspire more commonly used network operating systems, such as Cisco, Juniper, others, to consider the deployment model where routers, edge routers themselves can perform the origin validation, the RPKI cache validation function in order to do origin validation. I think this is one of many deployment scenarios. This is not necessarily the recommendation that will work for everybody, but I think there are some use cases, specifically in smaller ISPs, where it could be beneficial to take a page from this approach. Next slide, please. So everything is well with RPKI. It's being deployed, people like it, software is out there, we are close to doing things out of the box, but it appears there's just one last outstanding issue, and this is the matter of the ARIN RPKI TEL. It is a bit of an unfortunate situation that an organization that is supposed to operate in the best interests of its community, specifically its members, that they are not publicly distributing their public crypto keys. And I'm not sure what the immediate solution is, other than to keep lobbying and keep applying pressure directly and indirectly to this organization to get them to release their public keys to the public. But this is a measurable issue on the internet. A double-digit percentage of networks performing RPKI origin validation is not using the ARIN TEL because the ARIN TEL cannot be included in open source distributions such as OpenBSD. So we have to keep an eye out for this, and whatever security mechanisms we design next, we should keep in mind that we should make it hard for people to make the public keys unavailable. Next slide, please. So in summary, what I wanted to share with you from this slide deck is that RPKI is real, it's here, it's being deployed, and a lot of people are using it. So this means that we are now running in a maintenance mode where we have to keep our eyes and ears open towards the end users and the implementers of RPKI software. And that's all for today. Questions, comments, concerns, remarks can be either shared through the microphone or emailed to me directly.
Rüdiger Volk. Oops. Still Deutsche Telekom. Rüdiger Volk. Okay. Still Deutsche Telekom. I usually have to do some nitpicking about the language used. Precise use of language sometimes is actually helpful to avoid confusing people, even if the first use of precise language may confuse people who are used to imprecise use. The thing where I would want to do the nitpicking right now, with a perspective to attacking your last topic, is you are giving one map about RPKI deployment. I would change the headline for that to RPKI origin validation deployment. There are many ways to deploy and use RPKI, and there is at least one essential thing where a map like this could be given and would be useful, which is what parts of the address space actually are covered by certificates and ROAs, may be different. And for attacking your last topic, doing the maps showing the deployment that is visible through the public available TELs, as opposed to those to what is available with the secret ones, could be one of the nice things to push stuff.
I'll take it up with the team if
Yeah.
we can render some additional
Yes.
visual assistance.
Yeah. And the last word to the last to your last words, you were saying, well, okay, the TALs should be public. The IETF defined standards are assuming a single TAL that would be public.
Hi, this is Andre from ISC. I just wanted to say thank you for sponsoring the open source you use in production. I think it sets a good example for the community.
In the category of thank yous, it was Internet Society that helped extend LibreSSL with CMS functions. Actually, there's tens of companies and individuals involved in this project to get it going. The list is long, and that's pretty awesome.
Randy Bush, IJ Anarchist. I just want to say thank you.
Thank you for the kind words.
Thank you, Mr. Houston. It doesn't like this, so you'll have to hold it, or get shorter.
So the score is currently 2 BGP talks and 2 DNS talks. So DNS wins because this is another DNS talk. Next slide. I love it.
Oh, wait, there we go.
So the thing about the DNS, and I think BGP also shares this, is that these are distributed systems that spend a huge amount of time chattering to themselves. So in the case of BGP, there's an event. You might announce a prefix, there might be a link state up, down, and then there's sort of shit ton of updates just ripple throughout the rest of the network. And at times, trying to understand why your router is kind of having a seizure and what was the original event that is causing it is sometimes really hard to tell. Now, that's BGP, and you know, a fair deal of study has gone into that, and we still don't understand it, at least I don't. DNS is about the same. You might think that the DNS is kind of this transactional thing where your browser, your application is given some kind of name, so it asks a question in the DNS goes to hunt for the right authoritative server, and out pops an answer, right? So every question or query that's sitting inside the DNS should be able to be mapped to some original event that the user's driven. Nothing could be further from the truth. The DNS is like artificial intelligence. It just talks to itself. And at least 50% of all the queries that we see inside the DNS are basically shit. We have no idea why they're there or what's going on. And this is something we were looking at when we were looking at an area called aggressive NSEC caching. There's this kind of theory that DNSSEC is really, really good, but the really hard question is, what is it good for? And if you're not allowed to answer Dane, it becomes a really, really hard question, because if you can't use it for keying in TLS, what's it good for? And one of the theories was that, well, if it's not good for that, why don't we use it to actually change the way negative answers are cached in the DNS? Because the easiest way to bring down the DNS or parts thereof in a highly targeted fashion, and this is no secret, is basically random name attacks. You set up a large distributed system, you set up random labels across all of your little zombies, and you just hit the authoritative name server. Roy says I'm not allowed to say how. It's really easy. You just hit it, because the random names ensure that caching doesn't work. All of those queries go to the authoritative servers, and if the authoritative servers aren't well defended, they will melt. Now, what you really wanted was to get the recursives to come along and help you. So the first time you asked even a random subdomain name, it would go, no, I'm sorry, that doesn't exist. The only way you can do that, in theory, was with signed domain names and range-based answers. And whether it's NSEC or NSEC3 makes no difference. You can actually manage to deflect these attacks in theory. Now, that whole story and the answer is a different presentation, and that's not it. That's not what we're talking about today. But what we were talking about and looking at was a really simple thing. What happens when the answer is no? So we present to the user a DNS name, go and resolve this name, and it's our zone. And we look at the number of queries and what queries happen when the name does not exist. And the really odd thing was the person only got the name once, only once. It's inside an online ad. Control this. The user only exercised that name once and only once. Why are there more queries? Next. So we control the end user and we control the authoritative server. There are random labels flying around, so there is no caching. The thing is not signed, as I recall, or maybe it is, makes no difference. And we're getting a whole bunch of queries from the same resolver, from different resolvers, but this is weird. Why are we getting so many queries? Next. On average, over 60 million names that we used in this experiment, we get 142 million queries. In other words, no has to be said at least twice. No, no, and a bit more no. 0.37 of a no. And that's the average amount of time to say no. Now, it's really great that DNS queries are free, because if they weren't, someone would be making a massive amount of money, because, you know, this software is crap. Why is it doing this is sort of an interesting question. Next. So the naive expectation is that no means no. Browsers should understand that asking 3 times for a name that doesn't exist is kind of 2 times too many. But even out there in the bigger DNS, that's 1.37 times too many. So is this just the fact that folk who write DNS resolvers are lunatics? They could well be. I don't know. Their source code is Baroque. I have no idea what's inside it. There could be strange and wonderful loops doing this. Or it could just be we've created artificial intelligence deep in the DNS and just haven't realized the stunning beauty that we have created. That the DNS truly is a neural network and it's assumed a life of its own. Next. But there are some more prosaic reasons that sort of bed you down in what's going on. And part of, I suppose, the theory is that at various parts in the application stack, no one gives a shit about any other part of the application stack. Just do not care. And happy eyeballs is one of these, just do not care. I'm going to solve my problem and tough, you get more queries. Well, that's what you're built for. So oddly enough, happy eyeballs, if you're running dual stack, you double the number of queries instantly, because you don't wait for an answer from the first before you go to the second. You send off both an A and a quad A straight away, normally within 10 milliseconds of each other. And in our case, we saw 23% of these clients do 2 queries back to back. Interestingly, and you know, this is bizarre, 3% only asked for the quad A. Now, they're not a V6 only end host. We know this. The ad was delivered over V4. We're having a V4 conversation. It has dual stack, great, but it's asking for a quad A and not an A. My feeling is that it's serializing, not parallelizing. So it asks for the quad A, doesn't ask for the A record. It gets back an NX domain and goes, okay, the name doesn't exist, I will go away. 3% of the cases. 74%, only V4, which is about the same as the amount of V4 and V6 out there on the larger internet. So roughly expected. Next. So we can sort of start dividing things up a bit, and we sort of say, well, okay, let's just group these A and quad A queries together. And if we group them together, we saw 73.5 million DNS resolution events, but we still saw 142 million queries. So we've got our 2.37 down to 1.93 queries. Better, but the DNS is still weird. Next. under half the time, it just worked with either one query. Now, that might have been one A and one quad A, but it was just one query. The other half of the time, 51%, that query got repeated. And the average was 2.84. So there's a lot of queries going on. Next. And the real question is that an average misleading? Are there one or two resolvers that are doing an amplification factor of 1 million and everyone else being sane? Or is there sort of, most people are sort of randomly kind of weird? Next. So we looked at the distribution. 1,430 queries. I'm like, what part of no is a problem 1,430 times? Whoever wrote that software, you know, good on you. Work of art. Down on the other side, a large amount of folk requeried once, so it was 2 queries. A smaller amount twice. 32% of queries, though, were 3 or more repeats. So a third of the time, the DNS is going throb, 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 and the answer is always NX domain. Same name, same query type, just throb, throb, throb. Next. So does UDP just completely suck? So you're going to say, yes, it does, and I agree with you, UDP sucks. No, you had a problem, Jared, and it just can't wait, can it?
No, it can't.
It just can't wait.
Hi, Jared Mach-Akamai. So when you see these 3 queries in a row, do they have the same query ID and come from the same UDP port?
It's the same query ID and the same. Just hang on a second, Jared, and you will start to see what's going on, because it's more than you think. That was your yeah. No, so there's more clues going on here. Does UDP suck? Well, yes, UDP sucks, but it doesn't suck that bad. And the response was not big. It was only 603 bytes. And if I can't get a 603 byte DNS packet through the internet, I don't know what you're doing here. You should be fixing your shit, because quite frankly, if I can't get that through, I can't get anything through. So why are we seeing 51% of tests generating 2 or more? Next. So we started looking at the repeat intervals, Jared, and we started looking at the time between successive queries from the original epoch time. And, you know, there are these really strong peaks, you know. Next. So who writes a piece of DNS resolving software with a 370 millisecond timer, OpenDNS? Why did they use 370 milliseconds? Because that's a really aggressive retime rate. Why? Who writes software with an 800 millisecond retimer? Unbound. Who writes 1 second? Bind. So a lot of what we see here are actually signatures of the resolver folk making arbitrary assumptions about the UDP timeout intervals that have no relationship to reality, have nothing to do with anything else other than, it's just a number. And oddly enough, they all use different numbers, and what they actually cause is some degree of pathology of repeats, because these time intervals appear strongly in this requery signal. What's weird is, does UDP suck that much that the original answer never got there? Or is the resolver simply on this mindless path of got to repeat the query? Don't care if I got an answer or not, I just have to repeat this query. I'm a driven resolver. No clue. Next. So timers is one issue. The next is DNSSEC. It is a DNSSEC signed name. So it has an NSEC record. Aha. Is validating the NSEC a factor? And don't forget, these are unique names, and they're so structured that they're even in unique domains. So the validation has to be done every single time. So is DNSSEC causing this? So, okay, let's add another test. Let's go unsigned. Next. Wow. You have to get right up, all you have to get right up here to spot the difference between the blue and the red lines. No, the pointer won't help. Signed NX domains generate a lot more requeries going up over 5, 6, 7, 8, 9, 10, and so on. And the reason why is basically because of the time required to validate every single time The original recursive is going, look, I'm really bored about this. I'm going to ask you again because 370 milliseconds says I've really got to ask you again and again and again and again and again. So signing generates more load when the name doesn't exist because of validation. Next. And we can actually quantify this a little bit. When it's signed, the requery rate is 3.19 on average. With unsigned, it's 2.51. So around 12% of the time, it's DNSSEC that's causing the requeries. Next. So, okay, DNSSEC. Happy eyeballs, 23%. DNSSEC, 12%. Next. How many folk think DNS resolvers are just standalone boxes? Well, no one anymore, because they ain't. They're these weird things called load balancers, and they sit inside a whole bunch of, single resolver engines, except when the load balancers actually become load amplifiers, as is a case from this Taiwanese network, where the front-end load balancer decided to send the same query to every single member of 2 distinct subnets. And you look at those query times, every sort of every 100 milliseconds, I get another query from the same subnet but a different engine. Common as hell. Whoever runs this stuff has no idea what they're doing. And that a huge number of these distributed DNS resolver farms actually become DNS resolver amplifiers just because you can. Thank you very much. Next. How common? 70% of the requeries come from these shared subnet prefixes. So it's not the same IP address, it's a different IP address, it's a different query, but the original query has been forked out again and again and again across the entire subnet. Whoever runs resolver farms, whoever runs yours, fire them, because they're obviously shit at their job. Because this is really, really common. 70% of the requeries come in from these kind of odd resolver farms. Next. So I was kind of wondering, is this a no problem? I'm like, when I say no, do you not believe me? Whereas if I give you an answer, you go, oh, yes, good, fine. Is no worse than yes? So next, is the requery rate lower? Wow. If I give you an answer, you're more likely to believe it. But if you requery, if you get a real answer, you'll hammer the shit out of me. So that 39% of the requeries in NX domain signed become requeries, 3.19 queries per name. When it's a real answer, A and quad A, only 13% requery. Much, much better, guys. But your average is 5.81 requeries. What the? I'm like, you don't even like a good answer. There's this sort of subset of lunatics that kind of go, look, I don't care whether it's a no or a yes. I'm just going to ask and ask and ask and ask because, I can. So, yeah, whether it's a real answer or not a real answer, there's this phenomenal requery rate down there. Next. So that's the same graph. You need to be right up there to see it. But what you see is a DNSSEC signed name generates a lot more responses than a real name. But the real names, when they requery very, very hard. Next. So we can kind of put it out there inside of a single graph. This is the one that I showed you before. 42% do it once. Next. Happy eyeballs, I'd say about 10% additional load. Next. I'd put DNSSEC at 17% of the total load. Next. NX domain itself, signed NX domain, no versus yes, about 14%. Next. Insane stupidity down on the farm, about 13% of queries. And the next, wow, you guys are just inventive. I have no idea why else you're doing this, but, good on you. So, yes, this is the DNS for you. Next, nothing more. Thank you.
Yeah. Hi, Jared Mach again. So if you can hit the backspace key or something, Chris. So here, I don't see this showing whether or not this looks to be dysfunctional network behavior of packet replication in the networks, because I've definitely seen that before, especially with UDP, which is why I asked the prior question about query ID and the port numbers. And so I'm curious, is that the reasons Or is that
Jared,
something
it
else?
could well be. I couldn't think of any other deliberate pathologies that, I was smart enough to understand, but you've just uncovered one, and thank you. Replicated query packets. Something subtle, though, if the replication is happening between the recursive and the authoritative, I will see it. If the replication is happening earlier, it's actually not obvious what the recursive is going to do when it starts to get back-to-back queries and there's already a query in process. Good engineering says duplicate queries get held in a cache until the answer comes back. Reality says, all bets are off.
Sure. I mean, in the case of a resolver farm, I could easily see a subsequent query being load balanced differently.
Yeah.
But what I have specifically seen is I have seen network pathologies because people are either configured port spanning or mirroring or have active or passive taps in the middle for their own monitoring of the network that sometimes end up replicating packets. And it is especially harmful for UDP-based protocols like this, which is why I would urge you to look at that further in part of any subsequent research.
It's a good point. Thank you.
Jeff Oz, you certainly have plenty of interesting bugs here, and people could probably fix a number of these things just by changing
the people in the room created these bugs. I just watched them do it.
Oh, I'm sure. The one thing I'm here to respond to is UDP that bad? So I live in BFD for obvious reasons. UDP isn't always that bad itself, but the ecosystem that consumes it can be. So you can do your darndest to pass the packet all the way across the network, and it'll get to some part of your ecosystem, whether it's a firewall, a load balancer, host path for a VM, pick your poison of choice. And there's weird assumptions in the stack that it's okay to drop these things because it's meant to be unreliable and things will get through. And what that tends to have informed us as a protocol is that being adaptive about your load rate is actually very important. And the graph you're showing about the various implementations and the weird timing assumptions, constants are almost always wrong in some sense. An interesting line of inquiry might at some point be, is there a way to allow DNS to sort of actively signal back into the system, here's what a cadence should look like that would get you a better response rate?
That's a great question. And had you said that about 10 years ago, and the obvious answer is DNS over TCP. Why TCP? Because instead of a preset timer that tells you there's a problem, there's an acknowledgement timer. You actually understand round trip times, and when you're missing a packet, you wait for twice the time, et cetera, et cetera. TCP does a much better job of getting over packet pathologies because that's its job. Now, it'll withstand a loss rate of up to about 3 or 4%. That's why mobile networks work, as distinct from don't. So this is a good idea. But 10 years ago, when you said DNS over TCP, you'd be covered in arrows because obviously you're a heretic, you're a pagan, and you should be burned at some local stake. These days, it's fashionable to say DNS over TLS. Well, and everything will be cured and life will be wonderful. And if you're going ultra trendy, I'm going to mention the magic word. The magic word is DOE, and it just makes everything better.
So my heresies aside, my other big hat that I wear is BGP, obviously, and I spend an awful lot of time dealing with TCP pathologies. I think that TCP is the primary transport for DNS, which just simply compound a lot of very interesting problems. I don't really consider it part of the solution space.
Could you ever believe of a future where BGP worked over UDP?
I have some very entertaining slides about the history of BGP that has some pathologies about EGP that our elders would share about why fragmentation-based protocols are not good for routing.
Yeah.
Jen Linkova, two clarifying questions. So when you say yes, when you actually return some answer, does client get the page?
Oh, I'm not looking at that. Sorry, I just never went that far. I really am just looking at the DNS query logs at the authoritative server, and I'm just looking for repeats.
Because it's actually interesting. Is it actually client not getting the answers at all? I keep repeating.
Right. So you know, the wonderfulness of the DNS is there are so many points where the queries could get replicated. And, you know, it's in the load distributors, it's in the recursive engines, it's in the forwarding system, you know, let alone in the stubs, let alone in the application. And in some cases, the bizarre thing is your application might get an answer and go and get the web page, but somewhere deep in DNS land, some engine's going frob, because you can. We time everything, and every DNS query has a timer. 45% of all the queries we see on our servers are more than 2 hours old. A visible percentage are more than 3 years old. I'm like, I don't think a user's sitting there with the browser going, you know, I pressed this 3 years ago. I really am waiting for that page. So the DNS does take on a life of its own, and the web is not really relevant. Completion at the user level doesn't stop the pathology.
Okay, and the second question. So this 3%, when they only ask for quad A, you said you're sure they are not V6 only. So you mean you initiated communication over V4 without
Yes.
using DNS?
Yes.
Okay.
It's Tail. I came up with one request, but you've just added a second one in that I think it's probably best for all of us if we not refer to the throbbing DNS. But apart from that, I'm curious if you happen to repeat this experiment in the future, if you could also include the yes/no answer. That is a no data response, both signed and unsigned, to see how that might affect the data.
We've been wondering about refused, serve fail, NX domain, no answer, because this phenomenal amount of ghost queries in the DNS that just don't seem to have an obvious reason. And it's always been an issue, what responses encourage requery and what responses kill it flat. And we were working on a theory at one point that said NX domain is cached no. And the answer is, well, no, it's not. It's sort of hit me again. So, yeah, I don't know whether no data, refuse, serve fail, or any other response code would have different response behaviors.
Right.
It's worth a try.
That's mostly what drives my curiosity as well.
Yeah.
Hi, Jeff. Mark Smith. Another thought I had was that these persistent queries, even when you give them a good answer, are load balancers doing liveness checking. So they might present a single IP address to their client, but then they have a pool of upstream servers and they like switching quickly and so on. I hate them.
For various reasons, and I think it's probably a mutual hatred, the folk who build load balancers and the IETF have never met eye to eye. There is no standard, there is no spec, there is no behavior. This is a bit like the first weird and wonderful world of NATs. Everyone builds DNS load balancers differently.
Yeah, they screw with ICMP.
Some hash various parts, some do, you know, and so on. And so because a lot of the recursive resolver families appear to sit behind these wacky load balancers, the end result is a set of queries that do behave oddly.
Mm-hmm. I mean, Jared's question would possibly also explain this as well. It's just, yep, thanks for telling me you're there. I'll ask again in a few seconds. Thanks.
Hi, Nalini Elkins. I want to go back to the DOH and DOT question a bit. If we wanted to see this kind of behavior using DNS over HTTPS or DOT or whatever, where would be the points at which you would try to measure this? Because it's encrypted on the wire, right?
You're going down a completely different path. And a path that in the DNS is a path that doesn't have very many answers. The DNS is incredibly opaque. Our attempts, misguided as they came, of putting fingerprints in queries, otherwise known as client subnet, have been loudly met with accurate accusations of acute invasions of privacy. And so the DNS is resistant to any kind of realistic measurement of the things you're talking about. We can't see that clearly. You can see either end, but the middle is sort of a mystery.
Yeah, interesting. Thank you.
Rob O'Stein, couple of comments. One, the timeout issue with the ridiculously short retry intervals. Yeah, back in, you should pardon the expression, the 80s, we actually used retry intervals like, 2-3 seconds and stuff like that. And as near as I can tell, what changed it was essentially market pressure. It's basically an old version of the happy eyeballs problem. People whine when they don't get an instant response. And the idea that you're querying a global database and it might take a little while, well, screw that. I want an answer now, damn it. And, the vendors just kept cranking the numbers down until it got to the current insane levels. But it was already insane by the mid-90s, what Microsoft was doing then, and it hasn't improved.
No, you're quite right. And the problem was with UDP, there's no feedback.
Right.
You don't understand what you're driving in, so it becomes a number given to you from on high. Use this number for timeouts.
Yeah. The other thing is, I've not actually been in the DNS business for about a decade, but back the last time I was, our working theory about a lot of the insane query that just like nothing you can do will stop it was people behind stupidly configured firewalls, idiot with firewall. So they send lots of queries, they never get a response, so they send more queries. And they never turn anything off. They're like, well, it isn't working, so I'll add another thing, and I'll do this, and I'll do that. Oh, look, I'm finally getting responses. Good, don't touch it. And it just stays like that forever. I don't know how much of that you're seeing. I have no idea how you'd even detect that, but that was our theory at the time.
It certainly seems, and Chrome in its tests of liveness, which it sends off random names towards the root, there is this attitude in other parts that the DNS is infinite, is fantastically engineered, and works exactly as planned all the time. And people can just throw queries in at whatever magnitude they want, and there'll always be an answer. I wish it was so, but the fact that it isn't creates this astonishing sort of amount of tension between what application folk believe the DNS is doing and what operators see it's doing, and where DNS code vendors sit in the middle going, what the hell should I write next time? How to defend ourselves and folk who run our code. It's a tough one.
Aaron Falk, Akamai. Thank you for your talk, Jeff. 2 quick points and a question. Thank you for sustaining my belief that there's a lot of weirdness in the internet. I'm glad to see that hasn't changed. And I think that you gave the reason in, I think, your first couple of sentences, which is that it's free, right? There's, like many of our tragedies of the commons, there's really no reason not to keep trying. It would be interesting if there was a way to quantify the cost in your organization from the extraneous requests. And my question is, are you doing any sort of longitudinal measurements? Are you seeing any trends here, any periodicity? Is this changing over time? Are you planning on continuing the measurements to gain that knowledge?
We've been seeding the DNS with unique DNS names for 7 years now. And we see 7-year-old queries because the timestamp is inside the DNS name. So, there are just old queries out there. I always think the DNS is actually like long-term storage, that all you need to do is encode what you want inside a query and then just sit there and listen, and sooner or later you're going to get re-queried, and that's your read function. I don't know if it's getting worse or better, but certainly our perspective is we seed more names in, our repeat rate, the ghost rate just keeps on inexorably growing. At some point, we're going to have to walk away from the top level names that we're using because they're so polluted, the signal is getting lost inside the repeat noise. We know what we're doing because the names have meaning. But your server, which you've been running for years, which has a whole bunch of ghost queries, and you're seeing 1,000 queries a minute, is that 990 shit and 1 real? How do you know? No one does. The suspicion is that you are overwhelmed with your legacy and that real queries are actually extremely low, but they're masked out by this extraordinary property of the DNS to just simply memorize, repeat, and recycle. Quantifying that, difficult, but it certainly seems bad.
One question that occurred to me as I was looking at your analysis is there the potential that some of this is malware traffic that's using DNS queries as some way of probing the state of the network? reachability? Or
We see a lot of log replayers. So there is a massive business out there of capturing logs and then replaying it. And generally, they are relatively benign. But we also see a whole bunch of other things where are pathologies that are inexplicable. There was a DNS resolver in Jordan, another one in Guatemala, doing up to 20,000 queries per second for days of the same name. It's kind of, I'm sorry, what exactly is going on here, guys? You know, so the combination is just an amazing pool of awfulness. We've exhausted the line. Thank you very much.
Thank you. See you all in Vancouver. I sure will. And also the slideware should be available soon from the website.
Request for next time.
Yes.